In this video, you'll be exploring and developing the Pythagorean relationship, which can be helpful to determine a distance that cannot be measured directly. For example, suppose we wish to know how far apart boat ramps A and B are from each other. You will learn how the Pythagorean relationship can use distances that are known to calculate this unknown distance. Before we get started, there is some prior knowledge that is needed before exploring the Pythagorean relationship. We need to understand what 5 to the power of 2 means, which is also called 5 squared. 5 squared means 5 times 5, which equals 25. We could look at the factors of 5 and 5 as side lengths of a square. The area of this square is 5 rows of 5 to make up the 25. Because the 25 squares can be arranged in the shape of a square, it is called a square number. It is also why we call anything to the power of 2 squared. The side length of this square is 5, and the length of the side of a square is called the square root. Mathematically, we write that the square root of 25 is 5. So if we had a 7 by 7 square, we could express this as 7 squared, which is 7 times 7, or 49. We could also express that the square root of 49 is 7. To explore the Pythagorean relationship, let's use these squares to make various triangles. As we build triangles, think about what kind of triangle is formed each time. Here are 5 different triangles that were formed. How do these triangles compare to each other? How would you describe these triangles? One way to describe or classify triangles is by their angles. A right angle measures 90 degrees. An acute angle has a measure less than 90 degrees, and an obtuse angle has an angle measure greater than 90 degrees. Where do you see these angles in the triangles? The green triangle and the yellow triangle are called acute triangles because all of their angles are acute. The blue triangle is an obtuse triangle because it contains an obtuse angle. The pink triangles are right triangles. Let's take a closer look at these right triangles. How are the numbers related to each other for each triangle? You may have noticed that the sum of the smaller two areas equals the larger area. This is the Pythagorean relationship, and this is true for all right triangles. Let's consider any right triangle so we can generalize the Pythagorean relationship. In a right triangle, the longest side is called the hypotenuse. This side is described as opposite the right angle. The other two sides are called the legs of the right triangle. In discovering the Pythagorean relationship, we noticed that in a right triangle, the sum of the areas of the squares on the legs is equal to the area of the square on the hypotenuse. We can use variables a, b, and c to represent the side lengths of the triangle. So the areas of the squares are respectively a squared, b squared, and c squared. Therefore, we can express the Pythagorean relationship as a squared plus b squared equals c squared, which is also called the Pythagorean theorem. This is the theorem that we will use to solve problems involving right triangles. We can also express it geometrically as the sum of the squares of the legs is equal to the square of the hypotenuse. Before solving problems involving right triangles, let's take a visual look at how we can show that the Pythagorean theorem is true for any right triangle. In other words, This is a visual proof that the Pythagorean theorem is true. We need to show that the sum of the areas of the blue and green squares is the same as the area of the largest square. First, let's divide up the green square into congruent parts. Congruent means that they have the same size and same shape. Now let's move these pieces into the largest square. Finally, let's move the blue square to complete the area of the largest square. Because these pieces form an area equal to the area of the largest square, we can see that the sum of the areas of the smaller squares equals the area of the largest square. So this shows visually that the Pythagorean theorem is true for all right triangles. It is interesting to note that the Pythagorean relationship is not just true for squares on the sides of a right triangle, but any congruent shape. Now that we have learned about the Pythagorean theorem, let us apply this theorem with two questions from the textbook. What is the length of leg H in the right triangle? Give your answer to the nearest tenth of a millimeter. In this typical question, one measure of a shape, the length of side H of the right triangle, can be determined by simply knowing other measurements, the lengths of sides G and I of that shape. Before doing any calculations, try to estimate the length of side H. Later, this estimate can be used to assess whether your answer will be reasonable. Your estimate need not be precise. However, it is important that it is less than 9 millimeters, since side I represents the hypotenuse, the longest side of the right triangle. We can use our understanding of the relationship between the lengths of the sides of right triangles to find the missing length. We will approach this in two ways, geometrically and algebraically. Geometrically, we can draw squares on each side of the triangle. To find the missing length, we first need to find the missing area. The area of the square on side G is 5 squared, or 25 square millimeters. The area of the square on side I is 9 squared, or 81 square millimeters. The missing area is attached to one of the legs. We know from the Pythagorean theorem that the sum of the smaller squares equals the largest square. The missing area is what would be added to 25 to get 81, which is equivalent to subtracting 25 from 81. This tells us that the missing area is 56. Note that this number represents the missing area, not the missing side. Side H, then, is the square root of 56, which is approximately 7.5. Looking back at your estimate, a side length of 7.5 millimeters is reasonable. Algebraically, we can write an equation showing the relationship between the side lengths and the areas of their squares. Take a moment to think about the relationship between the sides G, H, and I. We know the Pythagorean theorem as a squared plus b squared equals c squared, but in this example, G and H are the legs and I is the hypotenuse. Substituting 5 for G and 9 for I gives 25 plus H squared equals 81. Subtracting 25 from both sides of the equation gives H squared equals 56. Again, this number represents an area. It's the square root that represents the missing side length. Let's explore another question. Anthony and Shalima are canoeing on Cultus Lake near Chilliwack. There are 2 boat ramps on the lake. How far is it by canoe between the boat ramps? This real-world problem from the textbook illustrates a key understanding. The The Pythagorean theorem can be used to determine distances that cannot be measured directly. Take a moment to estimate the length of the distance between the boat ramps. An estimate that is a little bit greater than 1,500 meters is reasonable since the distance by canoe is the hypotenuse of a right triangle. Can you describe the relationship between the distance by canoe and the two distances by road? The square of the hypotenuse is the sum of the squares of the legs. Let's let the distance between the docks be represented by the variable d. Summing the squares of 800 and 1,500 and then taking the square root gives a distance of 1,700 meters. There is a common mistake that students make when solving problems using the Pythagorean theorem. Notice that in one problem, the squares were added, and in another problem, the squares were subtracted. A common mistake is to add when one should subtract, and vice versa. If your child isn't confident in knowing whether to add or subtract areas, encourage them first to visualize the relationship. The comparable sizes of the squares can help them sort this out. In the first problem, the square on h is clearly smaller than the square on the hypotenuse, so one must subtract. In the second problem, the square on d is the largest square, so the known squares must be added. This video addresses several learning standards in the Mathematics 8 curriculum. In content, we looked at perfect squares and square roots. Your child will also learn about perfect cubes and cube roots. The primary content standard we focused on was the Pythagorean theorem. Several curricular competencies may emerge as your child learns and applies the content from this chapter. In our overview, we showed estimate reasonably when we encouraged you to make an estimate of an answer before calculating. The opening exploration with using squares to make triangles is a learning experience that develops understanding through play, inquiry, and problem solving. The problems we did for practice is demonstrating and applying this understanding. Finally, we used visualization when we used geometric squares to identify whether we should add or subtract the squares.